So we'll start by using the original function to sketch the equation of a derivative function. You've got a cubic here, normal looking function, pretty simple. We're going to use this to sketch the graph of f prime. Now, notice we don't have an equation, so we can't just calculate what the derivative is and graph it. We're going to have to use some information and some estimates based on the slope. Remember that the f prime function tells you the slope. The output of this function is the slope of the function we see. This is really a skill that'll be easier on pen and paper, but for now, if you have a ruler, pause the video and grab your ruler. I'm going to ask you to use it to compare a couple things on the screen. I'm going to switch over to paper. The instructions here are to use the graph of the original function, which is what we're looking at, to try and sketch a graph of the derivative function, and we're going to sketch that graph right on the same set of axes. Now, just because they're on the same set of axes doesn't mean they mean the same thing. Remember, the output of the derivative function is really the slope. So my strategy is going to be to set up a function table and then to kind of use those points to guide the shape that I end up drawing. We start with the x values, and then we're going to look on the graph and estimate the slope, and that estimate is going to become the y value of the slope function. In other words, my table is going to have x values and slope values. Let's start. -5, left of the graph. Here we go. My original function at -5. And this is where you're going to want your ruler. Take a look at the shape of this graph. Maybe it's helpful to compare it to a straight line. And think about what a tangent would look like. And keep in mind that we are estimating. So you may need to shift a little bit. And since it's an estimate, you really just take your best guess. So maybe this is cheating a little bit, but it looks like the slope is looking really close to up 3/1 if this line goes straight through that point. I don't really know, but it looks close enough for me. So I'm going to go ahead and say that at this point, -5, the slope of the function is a +3 slope. And sometimes what we'll do is we'll just sketch a little line right there to indicate that we've checked that slope and to estimate it. Next, I'm going to look at the x value of -4, and I'm going to do the same thing. Why don't you do this first? What do you think the slope is going to be at -4? Right, so when I look at this, to me that looks like that's a +1 slope. I don't know perfectly. I could compare it to my graph with the ruler, and I think that's close enough for me. At -4, we've got a +1 slope. As we continue, we're now going to go to -3. And we're going to estimate that slope too. We're just doing this visually. -3 is a little bit harder to see. For this one, I'm actually going to go ahead and draw a tangent line because this will help me out. And when I look at this tangent line, I want to imagine counting rise over run. So if I go over 1, this looks like it's not going up a full unit. In fact, if I go over 2, it's now looking more like a full unit. So I might call this a slope of 1/2, up 1/2. Notice how that's harder because the dots aren't falling on coordinate points, but that doesn't mean there isn't a slope, and it doesn't mean you can't estimate it. If you need to, try drawing out little dotted lines for yourself. This should look pretty close to 1 square, even though it's sitting in the middle of them. And this should look like pretty close to 2 squares. So the slope, -3, is going to be a +1/2. We move on. At -2, well, this is where the function is at -2. I'm going to use my ruler again, and when I make my comparison, this pretty closely looks like the negative version of the last slope. So I could do the same thing where I actually draw the tangent line and estimate, or I could just be a little bit approximate about this, and I could say, well, this looks like it's maybe going to be a -1/2 slope. We continue. -1. What do you think the slope is of this function at -1? Great, me too. I think it's a -1 slope. And my ruler helps me see that. It looks like it's going straight through these points when it crosses right there. Okay. And as I continue, 0 looks like it's almost the same slope. So this is a little tricky because technically it shouldn't really have the same slope, but we're just estimating, so I'm going to go ahead and continue to put a -1 there. And actually, +1 also looks like it's pretty close to a -1 slope, maybe a little shallower. And then we get to +2. When the x value of this function is +2, what do you think this slope looks like? This is one where I really would want to draw out the tangent line. And when I do that, it looks like we're going approximately 1 unit down when I go 2 units over. So that would be down 1 over 2. That would be a -1/2 slope. On the other side of the curve, it turns into a positive slope. And maybe it's +1/2, maybe it's a little less than that, but we are estimating. So I'm going to go ahead and say a +1/2 slope at x equals 4. To me, this looks like a +1 slope again. And at x equals 5, which would be right here, looking at that slope, it looks pretty close to a slope of 2. I notice that when I go over 1 unit, I end up kind of in between 4 and 5. And I started out kind of in between 2 and 3. So that looks like it's going up to over 1. Okay, so we now have a function table. This function table has x values and outputs, and we can graph them right here. I'm going to go ahead and just graph them as points. I'm going to switch colors so it's easier for you to see. The first point, -5, +3, would be right here. The second point, -4, +1, is right here. And this is just graphing points. You can imagine what it's going to look like. It turns out these are all the points. And then I can connect the dots. And they were estimates, so it's not going to be perfect. But I'm just going to do my best to make it a smooth function. I might get something like this. And a good way to end is to quickly reference the table that we just made. I noticed that with the graph I've drawn, in the first section of this graph, the original function's increasing, and the y values of the derivative function are above 0. That's as it should be. I notice that when there is a vertex on my original function, which happens twice, one there, one here, both times at the same x value, my derivative function has an x-intercept. And I didn't plan it that way. That's just how it turned out. When my original function is decreasing, which is in this middle section, my derivative function is underneath the x-axis. In other words, it's negative. And then at the end, my original function's increasing again, and the y values of my derivative function are above the x-axis. It can be really tricky not to get distracted by the derivative function increasing and decreasing. And it's also really tricky not to get distracted by the vertex of the derivative function. Use this same strategy to work out one on your own. I know that since you don't have this on paper, it's not going to be perfect. So you're just going to estimate. How'd that turn out? Here's the graph that I got. It's a little bit of a mess because I was drawing lines to estimate the slopes, but you can see the slopes that I was estimating here. Cross-reference it with yours. Although your numbers may be slightly different, at the very least, you should have the negative and positive signs in the same places that I do. Notice that for your graph and for my graph, the vertices of the original function correspond to the x-intercepts of the derivative function. There's another one here, and there's another one here. Notice also that when my derivative function is above the x-axis, which is there and in this brief section here, the original function is increasing here and here. When my derivative function is below the x-axis, as in it's negative, my original function is decreasing there and here. Good news, the last skill is slightly simpler. So we're now going to do the opposite. And when I say it's simpler, I may be waving my hands a little bit. The truth is just it's less precise, so you don't need as many points. We're going to do the opposite now. The graph that you're looking at is the graph of the derivative. In other words, the y values of this graph represent slopes. Slopes of what? Slopes of another function. We want to try and graph that other function. Unfortunately, this time, the derivative function doesn't give us exact information about the y values of f. So I'm going to use a strategy similar to what we do with piecewise functions. And you should make sure that you have that little table of relationships out, because I'm going to reference those. I'll start with what I know for sure. I know that when the derivative function has an x-intercept, my f function is going to have a vertex. So I'm going to make some notes for myself right down here at the bottom. And I'm going to start by drawing a little arrow to the place where x equals 0, and I'm going to write vertex. I expect the function I draw to have a vertex somewhere along this line. Similarly, it should have another one over here when x equals 8, and that's the same rule that I'm using. When the derivative has an x-intercept, my original function has a vertex. Now, it would be really nice if I knew whether they were max or mins. So let's use another piece of information from that table. In between these two vertices, my derivative function's y values are positive. What does that mean for the original function? That's right, it means that the original function is increasing. So all through the middle section of the graph, the slopes of the original function are going to be positive. It's going up. On the edges, on the other side of this vertex and on the outside of this vertex, the derivative function's y values are negative, and that means the original function is decreasing. Here and here. So I'm beginning to have a picture in my head. My original function's going down, it curves around, it's going up, and then it's going down again. Now, you may have sort of seen the shape that I sketched, but you shouldn't need my shape to tell you what kind of vertex this is. Think about it. You could either be a max or a min. Well, a minimum looks like this, and a minimum is when a graph goes from decreasing to increasing. A maximum looks like this. A maximum happens when a graph goes from increasing and then changes to decreasing. Using that intuition, this first vertex pretty clearly has to be a minimum. And this second vertex has to be a maximum. If you don't remember these rules from Algebra 2, you should stop and put them in your column and add them to cram. Now, the last step is to use a couple strategic y values from the derivative graph. Remember that the y values of the derivative graph indicate the slope of the original function. And this is just going to be a slight guide. So for example, I notice right here that there's a point at x equals 2 and y equals 3. When I think about that y value, I recognize that that means that the slope of the function I draw has to be pretty steep whenever it crosses the x equals 2 line. How steep? Well, I could sketch it out for myself. It's going to be this steep, up 3 over 1. Now, I don't know if the function's going to be down here or, frankly, where it's going to be, but I'm thinking about it being steep like that when it gets here. And it gets even steeper over here. It gets 4 steep. It's that steep. And then it kind of gets less and less and less steep to the point where here it's really just 2 units steep. I'm sketching these slopes at the bottom to help myself evaluate the graph I'm going to draw. It doesn't mean that my function is down here. I'm trying to interpret the information I have in front of me. There's really no right or wrong amount of interpretation to do. You have to make a choice. The last thing you need is you need to start somewhere. And the truth is there's no right or wrong way to start. In fact, this derivative graph has multiple correct original function graphs that would go with it. So you just pick a point. My habit is to always pick the point 0, 0 and work from there. So if I decide that my original function goes through 0, 0, I know this is a minimum, so I'm going to sketch the minimum here. And then I know that my graph gets pretty steep and it's going to have a maximum along this point. Now, if it's going to have a maximum over here, the maximum needs to be higher than this point because the graph has to increase all the way through. So I'm going to choose a point to be a maximum up there. And then I'm just going to connect the dots. Something like this. It's not perfect, but that's